Cambridge IGCSE Physics May June 2020 Paper 6 in one video. Question 1. A student investigates the balancing of a meter rule. Figure 1.1 shows the arrangement. There's a load of weight P which is x cm away from the pivot and another object Q at the other end that's at 90 cm mark of the meter rule. Part A. The student places the meter rule on the pivot at the 50 cm mark. He places an object Q on the meter rule with its center at the 90 cm mark, so it's 40 cm away from the pivot. He places a load of weight P equals to 2 newtons on the meter rule and adjusts the position of the load so that the meter rule is as near as possible to being balanced. He measures the distance x from the center of the load to the pivot. He repeats the procedure using loads of weight P equals to 3 newtons, 4 newtons, 5 newtons, and 6 newtons. All the values of P and X are recorded in Table 1.1. Calculate and record in Table 1.1 the values of 1 over x. You can see that as the weight of the load P increases, the distance away from the pivot decreases. Alright, for this question, we just need to do a simple calculation. 1 divided by 40 is 0.025, 1 divided by 27 is 0.037, and so on. Part B. Plot a graph of P y-axis against 1 over x x-axis. Start both axes at the origin 0, 0. First, draw the x and y-axis. X-axis is 1 over x and y-axis is the weight. Looking at the table, the range of x-axis is from 0.025 to 0.075, and for the y-axis, it's from 2 to 6. For our scale on x-axis, we have 5 big boxes here, so we can set one big box as 0.02. It's going to be 0, 0.020, 0.040, 0.060, 0.080, and 0.100. For y-axis, we have 5 big boxes, so we can set one big box as 1.2. When we plot it, it's like this. Part C. In this experiment, x max, the maximum possible value for x is 50 cm. Calculate 1 over x max. 1 divided by 50 is 0.02, so 1 over x max is 0.02. Use the graph to determine the minimum value of P required to balance the meter rule in this experiment. Show clearly on the graph how you determined this value. Remember, from this table, the higher the value of x, the lower the weight of P. In the first part of the question, they have given us the maximum value of x, and we found the equivalent in terms of 1 over x. Then they asked us to find the minimum value of P. This means that the maximum value of x will lead to the minimum value of P. We plotted a graph of 1 over x, so instead of using 50 cm, we need to use 0.02 that we have just calculated to find the minimum value of P. Show on the graph that you're using the graph and identify where it meets the y-axis. Part D. In this experiment, the width of object Q is slightly greater than the width of the meter rule. Explain briefly how you place the object Q as accurately as possible on the 90 cm mark of the meter rule. You may draw a diagram. So if the ruler is this wide, the object Q is wider like this, and we need to show how to put it accurately on the meter rule. They don't have a specific answer for this, it just needs to make sense. Well, you can measure the length of the object Q and mark its center. Then let's say its length is 4 cm. It should be placed on the ruler from 88 cm to 92 cm to make sure its center is exactly on the 90 cm mark. Part E. In this experiment, it is difficult to determine the exact position of the load that will make the meter rule balance. Explain briefly why this is difficult. The question is saying that it's hard to choose the exact point when the meter rule is balanced. This is because it doesn't stay balanced in only one point. For example, it may be balanced from 70 cm to 75 cm, so it's hard to obtain the exact balance point. Explain briefly how you'd find the best position of the load that will make the meter rule balance. Again, these questions are very ambiguous, no specific answers, and all are based on logic. You just need to find a point that's the nearest to being balanced. For example, if the meter rule doesn't move or move flat in its position and is almost stationary, it is considered as the best position. Question 2. A student determines the resistance of some filament lamps. Figure 2.1 shows the first circuit she uses. Power supply, lamp, voltmeter connected in parallel, and an ammeter to measure the current. Part A. Record the potential difference V1 across the lamp L1 as shown on the voltmeter in figure 2.2. It's the potential difference, so look at the diagram that says V. This is from an ammeter, it says A here. The answer is 3.5 volts. Record the current I1 in the circuit as shown in figure 2.3. Now we can use this diagram. The middle point is 0.3, so this is 0.38. Calculate the resistance R1 of the filament of lamp L1. Use the equation R1 equals to V1 over I1, include the unit. Just substitute the values in the equation. 3.5 divided by 0.38 equals to 9.21. The unit is in ohms. Part B. The student disconnects the voltmeter. She connects lamp L2 in series with lamp L1. She connects the voltmeter across lamp L2. She measures the current I2 in the circuit and the potential difference V2 across lamp L2. The current and potential difference are given here. Calculate the resistance R2 of the filament of lamp L2. Use the equation R2 equals to V2 over I2. Again, just substitute the values. 1.7 divided by 0.3 equals to 5.7. The student disconnects the voltmeter. She connects lamp L3 in series with lamps L1 and L2. She connects the voltmeter across lamp L3. She measures the current I3 in the circuit and the potential difference V3 across lamp L3. Now they have 3 lamps. Calculate the resistance R3 of the filament of lamp L3. Use the equation R3 equals to V3 over I3. 1.2 divided by 0.26 equals to 4.6. Again, it's in 2 significant figures. Part C. Calculate R1 plus R2 plus R3. Give your answer to a suitable number of significant figures for the experiment. Well, all our values of resistance were in 2 significant figures, so it will need to be in 2SF as well. The lamps are in series, so add up the resistance of 3 lamps. 9.21 plus 5.7 plus 4.6. It's 19.51, but in 2 significant figures, it's 20, so the answer is 20. Part D. Some students make suggestions about the results of the experiment. Suggestion A, R1 plus R2 plus R3 should equal to 3 times R1. Suggestion B, R1 plus R2 plus R3 should be less than 3 times R1. Suggestion C, R1 plus R2 plus R3 should be greater than 3 times R1. State which suggestion A, B, or C agrees with your results. Justify your answer by reference to your results. R1 was 9.21, and if we multiply it with 3, it's greater than 20. So R1 plus R2 plus R3 is less than 3 times R1, and our answer in part C corresponds with suggestion B. For justification, we can say that R1 plus R2 plus R3 equals to 20, but 3 times R1 equals to 27.63, so R1 plus R2 plus R3 is less than 3 times R1. Part E. Draw a circuit diagram to show the circuit used in Part B with all 3 lamps connected in series. When they said they were adding lamps L2 and L3, they were adding in series, so it would have been like this. And in Part B, the question said the voltmeter was connected across lamp L3. So instead of the voltmeter being here, it would be here connected parallel to lamp L3. This is the final drawing. Include the rest of the symbols such as the power supply and ammeter. Question 3. A student investigates the position of the image in a plane mirror. Figure 3.1 shows the ray trace sheet he uses. Part A. Okay, I'll show you this ray trace sheet on the screen and read out the question so I can explain while indicating on the diagram. The student draws the line MR. He draws a normal NL to this line that passes through the center of MR. This line is perpendicular to MR. He labels the point at which NL crosses MR with the letter B. This is the center of MR. He draws a line from B at an angle of incidence I equals to 30 degrees to the normal below MR and to the left of the normal. He labels the end of this line A. Angle of incidence to the normal, so this angle is 30 degrees. He places a pin P1 on line AB as shown in figure 3.1. He places another pin P2 on the line AB. Pin P2 is not shown in this diagram. He places the reflecting face of the mirror vertically on the line MR. So imagine that there's a mirror here on top of this line MR. He views the images of pins P1 and P2 from the direction indicated by the eye in figure 3.1. So there's a mirror here, 2 pins on line AB, one of them is not shown and you're looking at the mirror from this direction. On figure 3.1, mark with a cross a suitable position for pin P2 in this experiment. Mark any point on line AB but not too close to the mirror and at least 5 cm away from P1. I'll put it here. He places 2 pins P3 and P4 some distance apart so that pin P3 and the images of P2 and P1 all appear exactly behind pin P4. The positions of P3 and P4 are shown on figure 3.1. When you look at the mirror from this direction, you will see pin P4, P3, and the reflected images of pin P2 and P1. Draw the line joining the positions of P3 and P4. Continue the line until it extends at least 7 cm beyond MR. Alright, just follow the instruction joining these 2 points and more than 7 cm from this line. Part B. The student keeps pin P1 in the same position but moves pin P2 so that the angle of incidence I equals to 40 degrees. The pin positions P5 and P6 for the reflected ray are marked on figure 3.1. Draw the line joining the positions of P5 and P6. Continue the line until it extends at least 7 cm beyond MR. Okay, join them together and draw a line across it, again more than 7 cm from MR. Label with the letter Y the point where the two lines cross beyond MR. Write Y where they intersect. Draw a line from P1 to MR that meets MR at a right angle. Measure and record the length of this line. It's where it meets at 90 degrees, so it should be a vertical line like this. Measure this with a ruler and write it as your answer. The examiner will measure your line, so make sure you do it super accurately. For me, I drew it on a paper, I measured it, and I got 5.2 cm. Draw a line from the point labeled Y to MR that meets MR at a right angle. Measure and record the length B of this line. From point Y to MR, this is where they meet at 90 degrees. Measure this line, and again, remember it all depends on your diagram, there's no fixed answer. Just make sure you drew straight lines according to the instructions and measured it correctly. I got 5.2 cm, same as A. Part C. The student removes all the pins. He places pin P7 on the normal at a distance 6 cm from the front of the mirror. Line NL is the normal, so pin P7 should be somewhere here, 6 cm away from the mirror. He views the image of P7 in the mirror. He places pin P8 on the normal behind the mirror. He adjusts the position of P8 so that the image of the bottom of the pin P7 and the top of pin P8 seen over the mirror appear as one pin when viewed from all angles in front of the mirror. On figure 3.1, measure the distance x along the normal between P8 and the mirror. Simple question, just measure it with your ruler and put your unit as cm, since the question was keep using cm as well. I got 6.2 cm. Complete the diagram in figure 3.2 to show the appearance of the image of pin P7 and pin P8 as described in part C. Okay, you don't have to think too hard for this. This isn't a refractive block, it's just a mirror. The question said that the image of the bottom of the pin P7 and the top of pin P8 is seen over the mirror, appearing as one pin. So if I draw that, the bottom part of the pin will be on the mirror like this, and the top part of the pin will be above the mirror like this. Part D. The student expects the readings to show that the image formed in a plane mirror is the same distance behind the mirror as the object is in front of the mirror. Readings of A equals to B and X equals to 6 centimeters will show this. State whether your readings show that the image formed in a plane mirror is the same distance behind the mirror as the object is in front of the mirror. Justify your statement by reference to the readings. My readings for A was 5.2 cm and for B it was also 5.2 cm. And yeah, the reading of X was 6.2 cm, pretty close to 6 cm. So the student's expectation is correct. Your statement needs to match your results, so it depends on your results, but actually, you should be getting similar readings to me. Justification is that our readings of A equals to B. For me, it's around 5.2 cm and X equals to 6.2 cm, all within the limit of experimental accuracy. Part E. The student carries out this experiment with care, suggests a practical reason why the results may not be accurate. While the thickness of lines may affect the accuracy, if your lines are too thick, it may alter the length or the distance away from a point. You can also write this famous point for questions related to pins. There is difficulty in judging exact lining up of pins. You'll know if you have done this kind of experiment. It's quite hard to place these pins in a straight line. Question 4. Designing an experiment. A student investigates the effect of the color of the surface of a metal container on the rate of loss of heat from the container. She knows that black surfaces are better radiators of thermal energy than white surfaces and wants to investigate the effect of other colors. The following apparatus is available: metal containers each with the outer surface painted a different color, a thermometer, a stopwatch, a supply of hot water. She can also use other apparatus and materials that are usually available in a school laboratory. Plan an experiment to investigate the effect of the color of the surface of a metal container on the rate of loss of heat from the container. You should draw a diagram of the apparatus used, explain briefly how you would carry out the investigation, state the key variables to be kept constant, and draw a table or tables with column headings to show how you display your readings. You're not required to enter any readings in the table. Explain how you'd use your readings to reach a conclusion. 7-mark question. We need to include everything in this question, but there's a format to follow. First, we need to explain the method. Before we go on, we can draw the diagram in advance. Well, there should be a metal container with hot water in it, and we're going to measure its temperature from time to time with a thermometer. Always label your diagrams. We need to record the initial temperature first, and we're going to measure its temperature every 30 seconds to see how fast it cools. Next, we need to cover the independent variables. We're finding the relationship between the color of the surface and the rate of heat loss. The independent variable is the color of the surface. So repeat the experiment with 4 different colors, maybe with white, orange, blue, and black. Now state the variables that need to be kept constant. Most importantly, the initial temperature should be the same. If it starts from 90 degrees for white, the same for the others as well. Also, we should use a lid to cover the exposed area of hot water. We only want to find the heat loss by radiation. We need to prevent heat loss by evaporation. Okay, then we talk about dependent variable. The dependent variable is the temperature change. We have all the variables, and there's one more thing: to draw a table. The table must include the dependent variable, the temperature, because that's what we're measuring, and since we said we're going to measure it every 30 seconds, include a column for time as well. You don't need to include any readings. Finally, a conclusion. We have already learned this concept before. The greater the temperature change, the more it radiates heat and increases the rate of heat loss. So the greatest temperature drop among the containers show that it's the best radiator of heat. We've reached the end. Tell me what you think about this video. Your comments make my day. Thank you for watching. Subscribe for more IGCSE videos, and like and share my videos. Stay safe and God bless you guys. Bye!